Today, we are diving deep. We're not just talking about science. We're trying to unlock the source code of reality itself. We are opening up the fundamental rulebook for the entire universe, physics. I mean, seriously, what if you could get your hands on the instruction manual for reality? That's pretty much what physics is. It's a set of rules that explains everything, from why an apple falls from a tree to why stars shine in the night sky. It might look a little complicated at first, but you're going to see how beautifully it all connects. So, where do we even start with a rulebook this big?
Well, before you can build anything, you have to know the basic materials, right? You need to know the fundamental settings of our universe. These are the non-negotiable numbers that everything else is built on.
First up, c, the speed of light. Now, this isn't just how fast the photon zips around. It's the absolute, unbreakable speed limit of the entire cosmos. Nothing with mass can ever hit this speed. It's the universe's hard-coded top gear.
Next, we've got g, the gravitational constant. And what's wild here is just how tiny this number is. It's telling us that gravity is, believe it or not, an incredibly weak force. But because it's always pulling things together and it works over huge distances, it's the silent architect of planets, stars, and whole galaxies.
And rounding out our big three is h, Planck's constant. If g is the boss of the super big, h is the king of the super small. This tiny, tiny number is the key that unlocks the bizarre world of quantum mechanics. It tells us that energy isn't smooth and continuous. It comes in little, discrete packets called quanta. This is where reality starts to get wonderfully strange.
So think of these three constants, c, g, and h, as the universe's factory settings. They're non-negotiable. They set the stage for everything at every possible scale, from the tiniest particles to the largest galaxies. Every other law we're about to look at is built right on top of this foundation.
Okay, with our foundation set, we can move on to Act 1, the language of motion. Now that we know the basic settings, we can finally start to describe how things actually, move. And that brings us to kinetics. Now, kinetics is all about the what's and how of motion, not the why. How fast is that car going? That's its velocity, just the change in its position over a certain amount of time. Is it speeding up or slowing down? Well, that's its acceleration. This is the basic vocabulary we need to even talk about things that move.
And if kinetics is the vocabulary, then Newton's three laws are the grammar. The first law, inertia, is pretty intuitive. Stuff likes to keep doing what it's already doing. The third law is why a rocket can push itself through empty space. It pushes exhaust out the back, and the exhaust pushes it forward. But it's that second law. That's the one that really changed the game.
F equals ma. It looks so simple, right? 3 letters. But don't let that fool you. This is one of the most powerful predictive tools humanity has ever come up with. If you know the forces on something and you know its mass, you can predict its motion with incredible accuracy. This little equation is what took us from just watching the world to actually calculating its future.
So, okay, we can describe motion, but why do things move in the first place? What's the fuel? What's the currency that makes things speed up, slow down, or change direction? That brings us to Act 2, the cosmic currency of energy. This here is kinetic energy. It's the energy something has just because it's moving. And pay close attention to that little v squared. That's a really big deal. It means if you double your speed, you don't just double your energy, you quadruple it. That's why even a small, fast-moving object can have a massive impact.
The other side of the coin is potential energy. This is basically stored energy, the potential to do something. Think of a rock sitting at the very top of a hill. It's not moving yet, but it has a ton of gravitational potential energy. The second you let it go, that stored potential instantly starts turning into the kinetic energy of motion as it barrels down the hill.
And what's responsible for that potential? This law right here, Newton's law of universal gravitation. It's such a profound idea. Every single object with mass in the universe is pulling on every other object, and the strength of that pull just depends on how massive they are and how far apart they are. It's truly universal.
So, does this beautiful idea actually work in the real world? Oh, absolutely. The law of gravitation perfectly explains Kepler's laws of planetary motion. See, Kepler knew how the planets were moving from his observations, but Newton's law finally gave us the why. And that's the real power of this rulebook. It doesn't just describe what we see, it explains it. So far, we've talked about single objects, a planet, a rock, a particle. But what happens when you have lots of particles all interacting with each other? Well, that takes us to Act 3, the world of vibrations and waves.
At the heart of almost every vibration is something called a restoring force. It's a force that's always trying to pull a system back to its center, back to equilibrium. Hooke's law for a spring describes this perfectly. The more you stretch it, the harder it pulls back. This simple back-and-forth dance is called simple harmonic motion.
And this is where the magic happens. You take that simple back-and-forth vibration and you let it travel, let it spread out. What do you get? A wave. That's all a wave really is. A disturbance, a vibration, traveling from one place to another, whether it's ripples in a pond or sound moving through the air.
And of course, we can describe these waves with math. Take this equation for the speed of a wave on a guitar string. It looks fancy, but it just tells us that the speed depends on only two things: the tension, T, how tight the string is, and its linear density, mu, basically how thick it is. That's it. Change those and you change the speed of the wave. It's so elegant.
All right, for our grand finale, we're moving beyond the things we can easily see, like waves on a string, to the powerful, unseen forces that make our entire modern world possible: electricity and magnetism.
Now just take a look at these two forces side by side. It's kind of amazing, right? Their equations have almost the exact same structure. They both weaken with distance in the same way. The huge difference, though, is that gravity is based on mass, and it can only ever pull. The electrostatic force is based on charge, and it can either pull or push. And that one little difference is what allows atoms and molecules, and us, to exist.
And things get even cooler when these charges start to move. A moving charge creates a magnetic field, and it also gets pushed around by other magnetic fields. This formula, the Lorentz force, might look a little complicated, but it's actually beautiful. It perfectly combines both the electric force and the magnetic force into one single unified description. It's the ultimate expression of their deep connection.
And it is so important to get this. These rules aren't just for explaining static cling. This is the foundation of our entire technological world, from electric motors to the computer you're using right now. And here's the ultimate payoff. These very same equations predicted that waves of electricity and magnetism should travel at, you guessed it, the speed of light. Because that's exactly what light is, an electromagnetic wave. See? It all connects.
So from 3 fundamental numbers, we've sketched out a rulebook that describes our universe with breathtaking precision. These equations are one of humanity's greatest achievements. But are they the final word? Is the book completely written? Or are there still chapters we haven't even discovered yet? That's the question that keeps science moving forward.